Welcome back, and as James suggested, this is the quantum matter panel. Here our goal is really going to be to probe some of the material aspects of quantum research, as well as, and I think building well on some of the topics raised at the end of the previous panel, what this research and development might mean for the macroscopic and often very social world that we live in. In other words, we're going to talk about tools, including where they come from and what uses we might put them towards. I'm going to forego lengthy introductions because we have our speakers' distinguished bios available. I'm also selfish and want to save some more time for questions at the end. So the order we're going to go in, first we'll hand the floor over to Andrew from University of New South Wales, then Chao-Yang from the University of Science and Technology of China, and last but certainly not least, Stephen from the University of Sydney. I'll close then with a list of some of my own questions about their work as a way to catalyze our broader discussion. Therefore, without further ado, Andrew, the floor is yours.
Thank you very much, and particularly like to thank James and all the organisers for this great meeting. It's outside my comfort zone because almost all of the talks I give are government agencies and so on, but cutting out into this broad arena is a little bit different, and I think that I'm not going to be so brave as to try to be something different than I am and to go too far out into that zone. But so what I think I've been asked to do is to tell people a little bit about quantum matter, what are the properties of quantum matter and how can we use matter in a quantum way and apply quantum mechanics, quantum theory to do interesting things. And specifically, as you can see from the title, I'm going to be talking about quantum computing, which has been discussed a number of times today. And I'm going to talk about a particular way that we're doing quantum computing or looking to do quantum computing at our university together with a number of collaborators around the world. But I'll touch more generally at the introduction on some of the concepts of quantum computing. Some of them have already been talked about. Many of you in the audience will know about them, some perhaps to more extent than others, but I hope people won't be offended if I give a very basic introduction to those concepts just to put it into context. I'd like to thank our previous panellists, Mike and Shahina in particular, who gave a nice coverage of many of the key concepts and issues. Just about myself, I mean, I'm originally trained as a physicist, but these days I'm in the School of Electrical Engineering, and indeed our school is pushing very hard on the theme of quantum engineering. You already heard from Mike Bidgsook earlier talking about engineering quantum systems. Well, indeed, this aspect of taking quantum physics and actually building things out of it is a very big theme of what our university is interested in, and certainly myself. So, as promised, let's have a look at some of the most basic concepts of what is required to make a quantum computer. And the key concept is that we want to move away from the bits of information in conventional computers which are either a 0 or a 1, the binary encoding, and we're still, at least in the digital quantum computers that most people are interested in, we're going to use bits still of 0 and 1, but we're going to encode those on a quantum physical system. And at the bottom on the right, you see those balls. The arrow is meant to represent the axis of the spinning ball. In this case, it could be an electron or a nucleus. And so in a magnetic field that's pointed vertically, we have two possibilities for that spin, either down or up. And as most of you will be aware from your knowledge of quantum physics, if we try to measure that spinning electron, there will only be one of two possibilities that we will measure. We will either measure either the 0 state or the 1 state, as you see it there. But it's possible to put those into a quantum superposition, and by putting them into any fractional mixture of those spins. So if we visualise my thumb as being pointing down as a 1 and pointing up as a 0, then we can actually put that anywhere in between. And for example, at the halfway, if we think of my thumb traversing the surface of the Earth, and if we put my thumb on the equator, then we've got a 50-50 probability of measuring either an up or a down. And the magic of quantum computing really comes from the parallelism that's created when we use these quantum bits. So in conventional computing systems, bits of information are grouped together in what are called words of information. These could either have 16 bits, 32 bits, 64 bits, depending on how large our computing system is. And a word can hold a single integer, which and groups of integers can encode images, words, for example, and so on, as in language words. In a quantum computer, we will also have a register of bits, in this case quantum bits, and the power of them really can be summed up just by looking at the screen. If we imagine a quantum word that had 300 quantum bits in it, then that would be a string, when we measure it, of zeros and ones, but the number of possible states number of possible integers or pieces of independent information that we could store on those 300 bits is equal to 2 raised to the power of 300, which is approximately the number of atoms in the universe, a phenomenal amount of information storage on just 300 physical entities. 300 entities of quantum matter, be they single electrons, single particles of light. We're going to hear our next speaker is going to talk about encoding information on photons. So that's where the power comes from. I'm not going to go into the details of how we then use that in quantum algorithms, where we might hear a little bit later on, if we're lucky, from Steve. But I just want to highlight some of the applications of such quantum computing machines on this slide and on the next couple of slides, many of which we've already heard about. The top left, by the way, is not a quantum computing application. It's an application of quantum communications, which I think we will hear about in the next talk. So that's an application where we can increase security by using perfectly secure quantum states. The quantum computing applications are in the top right and the bottom left there, and the one up the top right is the one that we've heard quite a bit about already in the first session, and that is using quantum computers to decrypt public key encryption codes. The potential of quantum computers to do this first realised by Peter Shaw, who was a physicist and quantum scientist, probably one of the first quantum computer scientists at Bell Labs in 1994. And that particular algorithm and others that followed really kicked off the interest in security agencies for quantum computing because of their potential to give them the ability to break all modern public key encryption codes, at least as far as we know. And we heard about those applications, and we heard in some of the discussion at the end of the last presentations about the potential of using these new quantum technologies for good or for bad purposes, although I guess it's an open question and an ethical question as to whether the ability to do decryption and monitoring, it obviously can have both positive and negative aspects in society, and maybe that's a discussion topic for later. But I think it's fair to say that the thing that's stimulating most interest amongst the scientific community in quantum information is highlighted on the bottom left, and this is the applications of high-performance computing, and Mike Biersook already talked about that. This is the use of quantum computers to model real physical systems which are, by their nature, quantum mechanical. So the image on the right is an image of a so-called carbon nanotube, which is a prominent technological material that was only discovered a decade and a half ago, which creates an extremely strong material just a couple of nanometers across. It's effectively a new allotrope of carbon. I'm sure many people have heard of carbon nanotubes in popular science if they don't have a deeper knowledge of it. It's closely related to buckyballs, if people are familiar with buckyballs, which is sort of like the spherical version of this tube. But these materials and more complex materials, for example, DNA and proteins, once they get above a couple of tens of atoms, the number of permutations of how they can interact, how you can measure their properties, explode exponentially with the number of atoms involved, and super exponentially. And so it's really only quantum computers that have the potential to simulate these systems, and this potentially opens huge applications in biotechnology, pharmaceutical development, and so on. Because if, rather than having to do trials, endless trials, human trials on new drugs, imagine if you were able to actually simulate a particular drug that could attack a particular type of cancer or attack a particular type of virus, and do that all on a computer without any painful trials. This is really one of the promises of quantum computing. Not just that's in biotechnology, but one can also imagine designing completely new materials that have properties that could be beneficial to society, lighter weight materials, stronger materials. So those are some of the drivers for quantum computing, and maybe I'll come back right at the end to those drivers. And for those of you who are interested in learning about what are really the major quantum computing technologies under investigation, there's a really great special issue of Science magazine from 2013. I've got the details up there, but if you just Google for the future of quantum information processing in the journal Science, you'll find a great set of reviews that are very authoritative and talk about the main technology areas that are being studied. I think Mike also mentioned it was Richard Feynman, Nobel Prize winner for the discovery of quantum electrodynamics, one of the most accurate predictive theories to come out of quantum mechanics, and a brilliant all-round guy, obviously. Feynman came up with this idea or comment that there's plenty of room at the bottom. He was asked to comment particularly on the future of the computer industry and Moore's law. How much smaller can transistors go? What would happen with computing? And he talked about the idea of what if we went right to the bottom and actually used individual atoms and in particular individual quantum states. At the time, the idea, the details of quantum computing and full applications hadn't been worked out, but quite visionary of Richard Feynman. And since that time, there have been many areas that have been studied. Top left is superconducting qubits. Top right, ion traps, which are these are the type that Mike Bierce talked about. Some interesting work being done with optically accessible quantum states in diamond. Many people's favourite material, and also photonic qubits, which we're going to hear about next. But what I want to talk about, and here's, I have two questions. I was asked questions. My first question is a question that I will answer, or at least attempt to answer, and that is it possible to make large-scale quantum computing using the conventional technologies that we carry around every day in our hand? There are so many electronic items, processing items or memory items based out of silicon and silicon chip technology. Well, if we look inside one of these chips, for example, in a mobile phone, we'll see that there are millions, in fact billions of individual transistors that are used to control the currents of electrons in these devices. Imagine if we could actually take one of those transistors and turn it into a quantum bit. And as I'll show you in research in our lab, just over the past couple of years, we've been able to do this by taking one of these so-called MOSFET transistors and isolating a single electron inside that transistor and encoding information on its spin and in fact actually doing computations with these. So what would a quantum processor chip look like? Well, this is our vision for such a quantum processor. This actually has 400 quantum bits on it. The quantum bits are in the lower area. And the thing to take away is that it actually doesn't look enormously different from the microprocessor chips that we use today. It has different levels of connectors to address the different quantum bits and to perform computations. And so this is really a theme that we're focusing on in our group at UNSW, to leverage off silicon technology that already exists, combine it with quantum computing codes and build a full-scale quantum computer. I want to give a little bit of a historical perspective of how our group, but also in general, to a large extent, quantum computing research in Australia was kicked off. And it came from the paper on the left, published in Nature in 1998, from a scientist, Bruce Kane, an American, who now, by the way, works at the NSA Laboratory for Physical Sciences in Maryland. He came up with a really brilliant but potentially insane idea, which was to make atomic transistors effectively, in which you take a silicon chip. You see the material at the bottom, the light blue is silicon, very pure silicon, and you embed individual phosphorus atoms. And why phosphorus? Well, a couple of reasons. Firstly, phosphorus has one extra electron compared to the silicon lattice around it, and so you can use that electron as a quantum bit. And not only can you use the electron that surrounds the phosphorus, that's the kind of green fuzzy ball meant to be the electron wave function, you can also use the nucleus of the phosphorus atom as a potential quantum bit, a very long-lived quantum bit. It was known from fundamental studies of the spin properties in semiconductors like silicon for more than 5 decades, that the quantum coherence times of these spins could be very long, minutes in the case of nuclei, and seconds for electrons. And so the idea of Kane was to exploit these long coherence times, which are essential. If you're going to do quantum computing, you need your quantum bit, the information stored in it, to remain over the time of doing the calculations. And quantum states are very fragile. And the other big motivation for Bruce Kane is summarised by the photograph on the bottom right. This is a 300 millimetre or 12-inch wafer of silicon. That wafer contains probably about a few hundred Intel microprocessors, and each one of those microprocessors has around 1 billion of those transistors that I showed you earlier. So that scalability is a really key aspect of this research. The reason that Kane's vision at this time seemed so insane was there were really no technologies able to put individual atoms into a silicon chip. And so over the past decade and a half at UNSW and with our collaborators, the University of Melbourne and the University of Sydney for that matter, and other universities around Australia and around the world, we've developed two main technologies for positioning those atoms. On the right, actually on the left first is the more of an industrial approach, which is to fire the atoms in, to accelerate charged phosphorus ions and bombard them into the silicon, but to put just individual atoms in, which was a technology that we developed together with colleagues at the University of Melbourne. And the image on the right is an alternative approach. It was actually the first one that we conceived. And in that one, the idea is to use a small tip from what's called a scanning tunnelling microscope. And these scanning tunnelling microscopes, by the way, because I thought that Shahina's comments about atoms not being able to be seen, and indeed you can't see them with your eye, but you can actually see them with one of these scanning tunnelling microscopes. So in fact, the image on the bottom right shows rows of silicon atoms that are imaged with a very fine tip that basically just maps out the surface morphology of those atoms. I mean, that got the Nobel Prize for Binning and Rohrer at IBM Research in Zurich more than 3 decades ago, or around 3 decades ago actually. The idea here was to use that scanning probe to open up little atomic-sized windows in a surface hydrogen resist to allow phosphorus atoms to be positioned. And that has allowed some remarkable devices, single atom devices, to be made. These are all examples of single atom devices and also extremely narrow conducting wires, for example, just 2 atoms across, that have been developed by my colleague Professor Michelle Simmons at the University of New South Wales. This is known as a bottom-up assembly approach, where you're building the atoms effectively one by one. But the approach that myself and my colleague Andrea Morello and also my colleague at University of Melbourne, David Jamieson, developed was to use that ion implantation approach. And this has proved to be extremely productive in doing the first demonstrations of these types of quantum bits. I use this slide only as a prompt, but the idea, if you look at the bottom right, we see the blue and red arrow represent the spin up and spin down states of an electron on one of the phosphorus atoms in our device. And what we showed in this experiment was that we were able to measure whether the electron was a spin up or a spin down. So the red trace at the right is an electrical trace from one of the transistor devices on the chip, and that tells us deterministically that we've measured a spin up, whereas the blue trace, where we don't see that event, tells us that it's a spin down. So the ability to read the quantum state in one of these single atom devices is absolutely vital. And that's the reading, but we need to manipulate that spin as well. And the way we do this is by applying tiny electromagnetic fields which can access the internal quantum states of both the electron and the nucleus spin. We're looking from underneath our device and we see pools of electrons in the device, and the red dot is one of the phosphorus atoms. And in this device we can deterministically load an electron and put it on that atom in a spin down state or a logic 0. We can then apply pulses of these microwaves and we can rotate that spin in a quantum mechanical way to wherever we want. In this particular case, we've rotated it into a spin up, and as I showed you on the previous slide, that means that we can measure it. The way we measure it is that the spin up electron is able to tunnel quantum mechanically into that transistor and to turn that transistor on and give us a deterministic measurement. So the reason I wanted to show that cartoon was to give a bit of a visualization of what is now possible to be done with single atoms and single electrons, and how we can get a macroscopic measurement, an electrical measurement, that we can connect to wires to the outside world. Here in the data on the top right, what we're seeing is that an electron in one of these devices on the phosphorus atom being rotated from down to up and back again in a completely controllable way. And if we're halfway up that sine wave, that's the quantum superposition state of 50% up and 50% down, which is vital for making quantum computers. What I talked about at the start was, can we use more conventional transistor devices, such as the type that we see being held up on this silicon wafer by the old Intel CEO? Well, one of those transistors looks a bit like the thing up in the top left, and fortunately you can't read the scale bar, but the size of that transistor is 50 nanometers. And we're now able to make devices effectively similar to those in our research lab, but use them to confine just one electron, as I showed you earlier. And we did this actually only in late 2014 for the first time, again using these rotational microwaves to rotate the spin. And in fact, in this device, we can have not just one transistor, but we've actually lined 3 transistors up next to each other in this device. And we can make a qubit out of each one of those 3 transistors. So this is now starting to move towards this scalability, a new Moore's law, but now a quantum Moore's law with these quantum MOSFETs. And finally, just in October last year, we showed that we could put 2 of these quantum bits next to each other and perform a logic operation between them. This is the most rudimentary logic operation you can make between 2 quantum bits. It's called a controlled knot, where one of the qubits will change its state if and only if the control qubit is in a particular spin state. And with the 1 qubit rotations in this 2 qubit controlled knot, one can now put these together and can create any quantum computation that one desires. I hope I've at least given you an indication of what might be the answer to my question: can we use conventional electronics to make a quantum computer? I would suggest that there is a possibility. It's very challenging, and it's going to need a lot of money. And fortunately, and I just want to finish now returning to some of the bigger questions of quantum computing rather than the technical. And I think it's useful to see the investments that are being made by big companies like Google and IBM. And I would suggest that the reason that those companies are investing in quantum computing isn't for the military applications, because actually those applications, I think, will end up being much smaller in monetary value for them. It's really for those bigger problems that I showed at the start: protein folding, development of new drugs, and so on. And fortunately here in Australia, we've got a really active effort in quantum computing, as you've already heard from previous speakers and going to hear again in a moment. And we've been very fortunate to attract quite a bit of investment from our federal government as well. So with that, I will thank you for your attention. Apologise for going a couple of minutes over. Thank you.
Good afternoon, everyone. First, I would like to start by thanking James and all the organizers for inviting me to this beautiful place and the most interesting conference I have ever attended. So I'm from USTC, University of Science and Technology of China, which is located in Hefei. And we also have an institute in Shanghai, where we basically located now. And our university is relatively a young one, and it have particular strengths on physical science research. And you can see it's ranked as the first among all the Chinese universities for a few years. So this afternoon, I revised the title and some content of my slide to increase the clearness of my slide to fit into this conference. So actually, it's a special period of year from the Chinese calendar. This is a new monkey year, and today is the 4th day of the Chinese monkey year. When speaking of monkey, so if you walk in the street of Sydney, for example, you can see the flags along the street. When talking about monkey, so the most famous monkey for Chinese people is the Monkey King, which is immortal. And from this novelist called Journey to the West, which was written in the middle of 16th century. So in this novel, there are many also different kind of immortals who can listen thousands of miles away and who can see thousands of miles away. And for Monkey King, he can split into like thousands or tens of thousands monkeys and to do the fighting. And also he can travel like 10,000 kilometers away in like a second. So, I mean, as a child, when we were a child, we of course enjoyed watching these novels and movies, but also, I mean, we think about whether it's just some ridiculous imaginations. So there's some ideas in this very early novel that one day in heaven equals to 1 year in earth. So it was written in this novel. And of course, when we learn about relativity, we know this can happen. And also for these immortals like 1,000-mile eye and wind following ear, also it's not very common with the development of electrodynamics. And we can now then further open our mind to ask, whether maybe one day it will become, maybe we will think it's crazy today, but maybe hundreds of years later, it will also become possible for something like Monkey King's person split, and also, to travel like very, very far away in like just a second. But also in Star Trek series of movies in the West, people also dreamed of similar things, like when you are, fighting with, you are chased by some enemy, you disappear from one planet and you reappear in another planet. And this was a dream of to travel like very fast or, in ultra long distance. So in 1993, this dream, turns out to be at least work for microscopic subjects like electrons and photons as proposed by the six scientists, Charles Bennett and other people. And the key to this proposal is quantum entanglement, which was argued to question the completeness of quantum mechanics 80 years ago by Einstein and Schrödinger. So it turns out, with the help of quantum entanglement, the quantum state of an unknown quantum particle can be transmitted to a long distance away, but without actually physically transport the particle itself. The particle will disappear at this location and appear again in another location. Of course, when the idea was proposed, it was mainly theoretical interest. And also, as been talked about by the previous speakers, so the last few decades have witnessed great progress in not passive observations of quantum systems of quantum coherence, but rather to actively control or manipulate the quantum systems, as you see yesterday in Michael's labs and so on. And also, I think Michael already have mentioned that quantum theory has already given us so many things like our computer chips, microphone chips, but I think mainly they are based on the passive observations rather than the active control that we are doing now today. So being able to actively control quantum system give rise some technologies which was not available in the past, like quantum key distribution, which provides us a means to secure communications, and also for quantum computers, which Andrew has talked about. By taking advantage of the parallel of quantum bits, we can do some specific tasks much faster, exponentially faster than classical computers. Also, if you eventually have working quantum computers, you can link them together with flying photons to form a quantum network. And I think today it's still not very clear for the field to identify which system is a final winner of quantum computers. But eventually, if we want to build a quantum network, flying photons are naturally very good candidate to connect the distant quantum computers. Now I will introduce our center or our Institute for Quantum Computation based on University of Science and Technology of China. So the director and the chief scientist is Professor Pan, who couldn't be here today. And we have research efforts focused on multi-photon entanglement, solid-state quantum photonics, archicode atoms, quantum memories, and also we are just starting to also doing research on superconducting qubits and also single photon detectors. And some major project outside the lab, also major research effort of China. I also want to cover the research effort of the whole China. So a project led by Jiangwei Pan, doing now and will actually be finished in the middle of this year, is to build a quantum communication backbone network from Beijing to Shanghai with a fiber link exceed 2,000 kilometers. And it will have about 20 central relays in between. And these relays are still classical relays. And in the future, we plan to replace it with quantum memory built from, for example, archicode atoms or trap ions, which you can see from Mike's lab, use the light-matter interface. I mean, the difficulty or the challenge of quantum communication is how can we do quantum communication in the ultra-long distance to be practically useful. And as Mike also mentioned, that the optic fiber has revolutionized our communication network and also how human can get access to information. So for quantum communication, the challenge is, although the optic fiber has already very low loss, but because the quantum state cannot be cloned, cannot be amplified, so the secure communication distance without quantum repeater is limited to about 200 kilometers. So we have to use these repeaters. And another solution to greatly extend the communication range is through the satellite, because in the outer space there's no air, so there's literally no loss in the channel. So the photons can fly through like thousands of kilometers with negligible loss. So this is another way to efficiently extend the communication range. And this was also led by Professor Pan in China. And I think this will be the first quantum satellite, and it planned to be launched in the middle of this year as well. And also, it also will provide a playground to test quantum theories in ultra-long distance, which was not available before. So I will now introduce other quantum information processing research efforts in our institute. So I think photons are very easy to understand what is a quantum bit. So we know that photons are actually can be seen as electromagnetic waves. And we know that the electric field has a direction. So we can simply think that horizontally polarized photons as the logical 0, and vertically polarized the electric field as logical 1. And we can very conveniently encode arbitrary quantum superposition or a quantum bit in the polarization of a single photon, like in this one. And we can conveniently control them by using wave plates, like half wave plate and quarter wave plate. And we can use some linear optical elements like polarizing beam splitter to measure the state of a single photon, the quantum state. Like if they transmit, then it's 0. If it's reflected, then it's 1, because of this projective measurement. And we like photons because they are very robust, they are flying qubits, they are very fast, and they have weak interactions with the environment. So being useful for these quantum applications, as I mentioned before, quantum key distribution, quantum teleportation, and computation, it has some special list. we look for. One is being single photons, and the other one is to have high indistinguishability. So single photons can be calculated by the second order correlations of the electrical field, and can be measured by using this setup just to split the input photons into two ions. And if we see no coincidence, then it means its quantum is not classical, because we know that a wave can always be split into two channels, and you can always see both of them. But if we see photon as a particle, as a bullet, then it can only go to one ion. That means the photons has to be described by quantum. It's a single kind of like particle-like behavior. And being single is, in some cases, is not enough. We also need the photons to be identical to each other. When the two photons are actually identical, when the two photons are combined on a beam splitter, they will always exit on the same output. Two photons both in C or both in D, but never one in C and one in D. And this was a signature that single photons are actually quantum mechanically identical to each other. So one approach to produce single photons is by this nonlinear process called parametric down conversion. This was used for 6-photon entanglement when I was a graduate student. So in this process, we use a focused laser to shine on a nonlinear crystal, and with a very tiny probability, like 10 to minus 10, one photon will split into two, and these two photons are entangled. And we can further combine these entangled photons into multi-photon entanglement. For example, 6-photon entanglement, 10-photon entanglement, 8-photon entanglement, and 5-photon 10-qubit entanglement. In this way, we can establish a platform to do proof of principle quantum computing experiments to test if the algorithms actually work. So, for example, we can test Shor's algorithm, quantum error correction, and quantum simulation of annual statistics, and also recently to test some algorithm for solving linear systems of linear equations, and also for quantum machine learning. Another very interesting application of using this multi-photon platform is to do quantum teleportation. So we have imagined being, to travel by Star Trek, and the first experiment was done 18 years ago in Innsbruck, in Anton Zilling's group. So they have first demonstrated that a single photon state can be teleported away. And in the 18 years, it has been also tested in various different systems, like in trap ions and solid state, and also to go to long distance. Like we can manage to teleport now in 2006, the quantum state of 2 photons. And also we have managed to teleport state between remote atomic assembles, which consists of a million of atoms. And also we have moved to long distance. In 2010, on the Great Wall of China, we teleport a photon away to a distance of 16 kilometers. And in 2012, in the Qianhai Lake in the West China, we teleport a single photon with over a distance of 100 kilometers, which is also a pre-step for the quantum satellite, which proves that the attenuation can be overcome if we send a photon from the ground to the satellite. But in the past 18 years, all the experiments have only transferred just 1 degree freedom or 1 qubit of any physical systems. Like photons, it's a polarization. But we know that even for the simplest fundamental particles like a photon, it has multiple properties or multiple degree freedoms, like the frequency or the wavelength, the polarization, and the angular orbital momentum. And for atoms, it can be even more complicated. Like we know, for the simplest case, a hydrogen atom has many quantum numbers, the principal quantum numbers, the orbitals, the spin, and so on. So if we want to actually, to travel by teleportation, it means all the information of a particle has to be transferred away, not the partial information. So we start by thinking, how can we move from 1 degree freedom to 2 degree freedoms? and we choose the spin orbit information of a single photon, which is the polarization and also the orbital angular momentum. And the difficulty was to do this joint measurement, and this was enabled by non-dimensional measurement of two photons. Yes, this was named by the breakthrough of the year of last year. Our next step is how can we greatly increase the number of photons to be, actually practically, maybe not practically useful, but to do something more, interesting. And also, Michael has mentioned that the field of quantum computer hasn't been there for like 20 years. But until now, there's still, despite some claims from D-Wave, but there's no, very convincing quantum machine, which you put on a desk and you can say, for some task, it can beat like this guy, our best laptop. And this was our short-term goals. So for some specific simple tasks like boson sampling, we can, with only 20 photons, we can beat our classical computer. So we start to work with single photon source, and many physical systems can be used as single photon source, like trap ions, which we saw from Michael's lab today, but was kind of empty because it was just starting. When it's finished, it will be, I believe it will be even more complex than these photos, as you can see from David Weinland's group. And also there are some solid-state systems. The advantage of these natural atom systems is it have very good coherence. And the solid-state systems usually have quite some noise. And a perfect single photon source needs to fulfill all these very demanding checklist. And the solid-state system being very noisy sometimes is because of incoherent control. For instance, this non-resonant optical excitation. And we have recently overcome this non-resonant excitation into truly resonant excitation, taking the solid-state artificial atoms as people do in atomic physics to drive it resonantly. And this gives us very pure single photons with 97% indistinguishability. And further we climb up to 99.5% indistinguishability. And very recently we can also combine the high purity and with the high efficiency. So now we can couple over 10 million single photons into a single mode fiber, and we detect about 3.7 million photon counts per second using the quantum dot, which is the brightest single photon source in the world. And meanwhile, it can preserve very good quality of the indistinguishability. So this enables us to move into multi-photon entanglement, not based on the nonlinear optics, but based on these tiny quantum dot. And it has the potential to scale up to 20 or even more single photons to demonstrate some specific quantum machine. I think it can be still defined as quantum simulator to beat our classical computer. I think I have run out of my time, but I also still want to thank my collaborators, like Jiang Wei-Pan is the director of our institute, and Sven Hoflin from Würzburg, who provides us high-quality quantum dot samples. So this is my students and one postdoctor, and these are some photos from the lab in Shanghai, and we welcome to all of you to visit when. Okay. Thank you for your time.
Well, I want to thank James and all of you for giving me the chance to talk about my favorite topic in the world, which is why quantum. And I want to thank the previous fellow panelists for really motivating what I wanted to talk about here, which is that the development of quantum computers, I want to emphasize this, there's a real shift in the field right now that the development of quantum computers is believed to be inevitable. We really think that we can build it. It's going to be a lot of work, but we're going to be able to build it. And the debate now is really what are the approaches to do that and what systems. I haven't been in Australia long enough to be a betting man, so I won't pick one. But the feeling that it is inevitable is really out there in the community. And that really impinges on one of the main topics of this workshop, which is, can the laws of quantum physics really apply to the macroscopic? And if we build a quantum computer or other sort of very large-scale quantum technologies like these quantum networks, then it will be a definitive yes answer to that question, because a quantum computer running a computation is very much a macroscopic thing. It's solving a problem like factoring a number or designing a drug or doing real-world macroscopic problems. So if we can build these quantum computers, then we really do have an example of macroscopic coherence. But beyond that, we think it's going to be very useful and potentially quite disruptive. Now, I'm a theorist. Unlike the previous speakers, I'm a theorist, and I have a different job than trying to make a quantum computer happen and to put one together. Part of my job and part of my interest is trying to figure out what to do with it. And we have a lot of ideas of what quantum computers are good for, but we don't feel that we have a good understanding of really the extent of what they can do. And it's in part because we really don't understand them at all. We heard earlier that, yes, there's still a lot of debate within the community of physicists about what the rules of quantum mechanics that we understand mathematically very well actually tell us about what is going on in a quantum system. And that's really the focus of my question. What's going on in a complex, very large-scale quantum coherent device like a quantum computer that gives it such power? And to answer that question, we need some understanding of what it does. We heard Andrew describe quantum computers as having some sort of quantum parallelism. This is a very widely held view of what quantum computers do. They're doing many, many parallel classical computations at the same time, and more than that, that there's some interplay between those different computations that's really enabling you to do something much more powerful. But when you try to make that concept precise and to use it to say, oh, I'm going to design something that makes use of that parallelism to do something useful, it's really quite hard. And so what we really need as theorists are better tools for understanding what's going on inside the box of what a quantum computer might be. And when I say what's going on in the box, I don't mean like this box. This box, we don't know what's going on in that box because it's commercially protected and they won't let us look inside, but broadly we think nothing. But there are conjectured quantum devices which we really think are going to outperform classical devices, and we would like to see what's going on inside and to have some understanding of what that is. And this is not a new question. I want to relate this to some of the oldest foundational questions in quantum mechanics. So I'm going to go back to the original debate, which was it's really the same question, just cast in a different era, when they didn't have the experiments and they had to think more abstractly and with Gedanken experiments about what quantum mechanics is really telling you. And this is a great story of one of the great debates in the 20th century between Einstein and Bohr as they hash out what are the meanings of the mathematical objects that appear in quantum mechanics. And Einstein and Bohr had extremely different views on the meanings of the basic elements in quantum mechanics, in particular this wave function, which is precisely the type of thing that we think is interfering and allowing for these different parallel computations in quantum mechanics. Bohr's view is that quantum mechanics told you everything. His quote is hard to unravel in typical Danish style. What exactly does he mean by that? A quantum mechanical description of physical phenomena would seem to fulfill within its scope all rational demands of completeness. Unraveled a bit and paraphrased, he means that quantum wave function is the whole story. That's everything. It's not about describing something that's going on out there. It's not something about your information in your head. It's just a mathematical tool that has all the possible data in it, and you use it to calculate predictions of outcomes at the end of your experiment. And there's nothing more to it, and you shouldn't think too much harder about it, perhaps. Einstein didn't like this view at all. He couldn't believe that there were rules that had inherent indeterminism in them, and famous for his quote, "God does not play dice." He really believed that this wave function, this psi function, in quantum theory was an incomplete description, that there was a deeper theory going on that described what's out there, the real world. And this wave function is more attached to our description about it, and it's a description where our knowledge is incomplete. We don't have all of the details. And so when we talk about concepts like quantum uncertainty, that it's really our uncertainty there that's occurring. And that he had hoped to explain things like entanglement and so on through just correlations between events of which you don't have precise certainty about. So these are very different views of what the basic elements of quantum theory are. And I'm not going to summarize the whole argument. It culminated in the great EPR paper coming out entitled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" by Einstein, Podolsky, and Rosen. The rebuttal, in a sense, by Bohr is, can quantum mechanical description of physical reality be considered complete? Two very alternative views with that same question as their motivating, as the motivation for their work. And despite the fact I challenge anyone to read Bohr's paper and really get some deep insight as to what he was arguing there, but broadly, the Copenhagen interpretation, which is the encapsulation of Bohr's views there, really came out that we shouldn't ask those questions about whether this has something to do with our uncertainty or what is the real state of affairs that's occurring. We should just use this as a calculational tool, and we get our answers, and then we don't ask any more detailed questions than that. And so I find it surprising at the time that Bohr won this debate, and that Einstein's view of what quantum mechanics could be like was sort of put aside. It was vindicated later when we saw things like Bell's theorem that really said that the type of thing that Einstein wanted as a more complete theory underlying quantum mechanics simply could not exist and explain all the quantum phenomena that we have. But rather than saying, well, let's take elements of Einstein's very coherent and very compelling argument and say, how can we modify them and adapt them and use them to gain some enlightenment as to what's really going on, we completely went away from that view and took up the Copenhagen interpretation, where you really just don't ask these questions. I find that this notion is very well encapsulated with the thought experiment, Schrödinger's cat. So I'll briefly explain this to you in case you haven't heard this one before. It's one of the most famous and most morbid thought experiments in quantum physics. You put a cat in a box together with a vial of poison that will be triggered by some atomic decay or some nuclear reaction. The idea here is to try to amplify the strange quantum effects that occur in that atomic decay up to the macroscopic. Based on that decay occurring or not, or being in some strange quantum superposition, you find that the poison is released or not, and the cat is killed or it stays alive. And if you don't look in that box, then the cat is in this strange superposition of being alive and dead, that you have quantum mechanics made macroscopic. And Schrödinger put this forward as really a Gedanken experiment to show that the idea is absurd. You can't have a cat in a superposition of alive and dead in the box. Now that we're building a quantum computer, we think that perhaps you can. And so the question really comes around to what does that actually mean? What does it mean to say that the wave function of this poor kitty is a superposition of alive and dead? Some physicists, you ask them, they say the cat is both alive and dead at the same time. Or the cat is either alive or dead, but what it actually is not an element of reality. It's only determined once I look at it. And you really see the role of the observer coming in as an active agent in this process of trying to illustrate the meaning of that superposition of that macroscopic object. So that was a great thought experiment that went on for a long time. And I want to argue that this is exactly the thought experiment that I posed at the beginning, which is trying to figure out what's going on in a quantum computer, to say what is actually occurring inside that box when I say a quantum computation is occurring. There's superposition, there's entanglement, there are all these bizarre quantum properties occurring in this system. But to understand really how I can use that to harness new algorithms, I'm going to need an understanding of what that means, about how that you can think of perhaps different classical computations occurring at the same time, much like we might say the cat is both alive and dead at the same time. You can imagine further thought experiments involving Schrödinger's cat where you can put it in this superposition and then return it to either alive or dead with certainty. And you can imagine that same type of thing in a quantum computer as well, that I can combine those superpositions in a way to make one computation or another come out with certainty. The very same questions that drove Schrödinger to ask, what can I say about this cat and what does it mean to be in a superposition, we're now asking about quantum computers. But the motivation for the question takes on a new urgency because it's not a thought experiment about understanding the hypothetical of what if quantum mechanics applied to the macroscopic world. They thought at the time that maybe it could never. Now we really think we could build it. Now we think we can build a quantum computer, and that question becomes very relevant and urgent for us to answer, just to explain what's going on, but also to develop new algorithms for quantum computers. So I'm just going to, forgive me, in the last few minutes, sketch out an outline of some research that we've been doing at Sydney, which is trying to turn this back around and to go back to the origins of that debate in terms of the role of the quantum wave function in describing a quantum system. Is this something that is talking about the reality of the system? Is this something that's talking about our information about the system, or something that involves both? Or should we not ask those questions at all? This is a very good day for saying maybe Einstein was right. And I want to say that there's elements in what Einstein was arguing that are still advantageous for us to use. He was seeking a theory from which all of the strange properties of the quantum wave function could be explained just by perhaps lack of knowledge or uncertainty in our knowledge of events. We now know that such a local theory is hard to develop, but we want to apply that theory as far as it will go and see what are its limitations. And that's really what we've attempted to do for a model for the quantum mechanics of quantum computing. We've tried to develop a model that whenever things are behaving classically, it is providing a theory that is like what Einstein wanted. There are classical computations going on that are just hidden from us. And when we see superpositions, we mean that it's going to be one or the other, and it's our lack of knowledge which is encoded in those superpositions. That can describe some things that are going on in the quantum computation, but there are other aspects of quantum mechanics which no such theory would be able to describe. I put them down as genuine quantum computations which make use of things like Bell's notion of non-locality. We can't incorporate those things into such a theory. Can we find a broader theory that can include those things as well at the expense of losing that interpretation only for those aspects, but maintaining it for those things that we can understand? And we've developed exactly a theory like that. The advantage of this theory is that it really identifies now the things that are outside the domain of this classical explanation that Einstein wanted. There are elements of quantum theory outside of that. It identifies those things as a resource that we can use to do interesting quantum technologies that are not possible classical. These are resources that can be quantified, consumed, and exploited within this theory. And then rather than viewing them as a mystery or an obstruction to our understanding of quantum mechanics, we have to now internalize them as resources to be exploited. I think I'm out of time, so I'll wrap up there. Thank you very much.